Have you ever stopped and wondered why those huge dam walls are always way thicker down at the bottom? Or maybe how just one person, seems to lift a whole car super easily at a garage?
Yeah, with a hydraulic lift.
Right. And what about mosquitoes? How can they just walk on water when, well, we definitely can't?
Yeah, good question.
These aren't just weird facts, are they? They point to something deeper. So today we're doing a deep dive into fluids, liquids, and gases, and their kind of surprising properties.
Exactly. Our mission today is really to unpack the physics behind these things you see every day. We want to turn those moments into satisfying aha moments for you.
Love it.
We'll look at hydrostatic pressure, Pascal's law, buoyancy, and that weird skin on liquids called surface tension.
Okay, let's start with dams then. That thickness at the base. It's not just for looks, I'm guessing. There's a solid reason.
Oh, absolutely. It's all about pressure. Specifically, hydrostatic pressure. That's the pressure a fluid exerts when it's just sitting there at rest. And the key thing, the really crucial part, is that this pressure goes up the deeper you go. It increases linearly with depth.
So more water on top means more push at the bottom.
Precisely. More weight pushing down. So the dam wall needs that extra thickness, that extra strength down low to handle the much, much greater force.
Makes sense. And it's not just water pressure, is it?
Yeah.
I was looking through the notes. The air around us, atmospheric pressure, that's powerful too.
Oh, incredibly
I
powerful.
like that experiment, O.V. Garrick, with the copper halves.
The Magdeburg hemispheres, yeah, classic demonstration.
He pumped the air out, sucked them together, and it took, 8 horses pulling on each side to get them apart?
That's right. Shows you the immense force air pressure exerts from the outside when there's nothing pushing back from the inside.
Wow.
And it's measurable, too. Corricelli, he figured out how to calculate it using a mercury column. About 76 centimeters of mercury.
That translates to?
It's about 1.01 times 10 to the 5 newtons per square meter. Think of it like a small car pressing down on every square meter around you.
We're just used to it, I guess.
Yeah.
Okay, so fluids push when they're still, but what about when we push on them? How does that explain lifting a car? Or even stopping a huge bus with just your foot?
Now you're getting to Pascal's law. This is really cool.
Okay.
Pascal basically said if you have an enclosed liquid and you apply pressure anywhere in it, that pressure gets sent everywhere inside the liquid, completely undiminished. It doesn't weaken.
Undiminished. So the pressure spreads out evenly.
Exactly. So in a hydraulic system like that car lift or your car's brakes, you push on a small piston. Small force, small area.
Right.
That creates a pressure. And that same pressure acts on a much larger piston on the other side. Same pressure, bigger area.
Means a bigger force coming out.
You got it. Force multiplication. That's how a little push on the brake pedal can generate enough force to stop tons of metal.
That's incredibly clever. Okay, another one. Why is it so much easier to lift something heavy, say a big rock, when it's underwater compared to in the air?
Good observation.
Or how does a giant hot air balloon just float up?
That takes us to buoyancy and the famous Archimedes principle.
Archimedes.
So buoyancy is just the upward force that a fluid pushes on anything submerged in it.
Like the water is helping you lift.
Kind of, yeah. And Archimedes figured out exactly how much help you get. The buoyant force is equal to the weight of the fluid that the object pushes out of the way the fluid it displaces.
Okay, so if the object displaces a lot of water weight.
If the weight of the displaced fluid is more than the object's own weight, it floats. If it's less, it sinks. If it's equal, it hovers.
And the story goes, he figured this out in the bath, right? Shouted, Eureka!
That's the legend. He saw the water level rise when he got in, realized the connection between volume displaced and buoyancy.
And then used it to check if the king's crown was solid gold or not, by checking its density using displacement.
Exactly. A brilliant insight from, taking a bath.
Okay, one last strange observation from the materials. Water droplets, or even mercury beads. Why are they always, spherical? And back to the mosquitoes. How do they do that walking on water trick?
Both of those come down to something called surface tension. It's a property of liquids.
Surface tension, okay.
It happens because of the forces between the liquid molecules themselves, cohesive forces. Inside the liquid, a molecule gets pulled equally in all directions by its neighbors.
Right, balanced out.
But a molecule right at the surface doesn't have neighbors above it pulling up. So there's a net pull inwards and sideways.
Ah, so they all get pulled together tightly at the surface.
Exactly. It's like they're creating a stretched membrane or kind of elastic skin across the surface. This skin naturally tries to pull the liquid into the shape with the smallest possible surface area for its volume.
Which is a sphere.
Precisely. And it's that same skin, that surface tension, that's just strong enough to support something really light, like a mosquito, letting it walk across without breaking through.
That's amazing. So these basic ideas, pressure, Pascal's law, buoyancy, surface tension, they explain so much, from massive dams to tiny insects.
They really do. If you step back and think about it, these, well, relatively simple physical principles underpin countless things we see, both natural phenomena and amazing feats of engineering.
Understanding them definitely gives you a new lens to see the world.
Absolutely. It provides a much deeper appreciation for the invisible physics that shape everything around us.
Totally. So next time you see a raindrop, maybe clinging to a window or watch a huge ship floating easily on the sea, just, take a second. Think about those forces we talked about. What other everyday things can you maybe explain now using these ideas about fluids?